All right, so plan for this week, just as a kind of a heads up as to where we're headed. Last week, we took one day to go over the properties of exponents, power to a power, when do you add the exponents, when do you multiply the exponents, things along those lines. Then we took a day, and this is the 6-1 worksheet that I want to go over, on simplifying radicals. Simplifying square roots, cubed roots, fourth roots, all those kind of things. And that's the lesson, the 6-1 worksheet that we're going to go over here in just a second. The next step, here's kind of the next idea. Today, we're going to look at how do you multiply and divide radicals. Okay, square roots, cubed roots, all those involved. And then what we will do in the next section on Wednesday will be kind of just operations in general. Of all right, now we're at the point where how do you add radicals, how do you subtract radicals, kind of putting it all a little bit all together at that point. Okay, so that's where we're headed. So objective for today is to multiply and divide radicals. And let's start, like I said, with any questions you might have had from the 6-1 worksheet here. Okay. Let's start with the front side. See if you had anything here at all. Here you were just going through and actually evaluating these radicals, trying to get actual answers. Do we have any questions on 1 through 12? Any questions on that at all? No, we're doing okay on those. Biggest thing for this, by the way, is really you're just looking at, this is just trying to get you used to square roots, cube roots, all those kind of things. And remember, when you do a square root of the fraction or a cube root, doesn't matter what the root is, you take the root of the top and the root of the bottom. You do it separately, okay? So just a heads up there. So same thing down here. Cubed root of 8, cubed root of 125. Therefore, this one ends up being 2/5, okay, as your final answer. So just a heads up there. All right, well, if there's no questions on that side, then let's go to the back side and see if you had any questions on any of these. I bring those up. Any of the 13 through 24, these were more the simplifying ones, where you had variables involved. Anything that you want to go over. Now is your time to ask if you're struggling. Okay, please ask if you're struggling. Well, we're doing okay. Okay, well, if we're doing all right, then I'm going to keep moving on. So here's what I want you to take out something to take some notes on then. Take out a sheet of paper, and I don't have a real long lesson today because it's fairly to the point. But there are a few examples that I want to take you through here. So here's the idea. So we're going through, like I said, we're multiplying and dividing radicals today, regardless of whether it's a square root, cube root. You can see previous chapters we multiplied square roots. Now we're multiplying cube roots, fourth roots, things like that. Just like we did in the last chapter where we did quadratics and then we ended up doing third degree, fourth degree, that kind of idea. Now before we did square roots, now we're doing cube roots, fourth roots, fifth roots. Okay, it's the same general idea. So previous chapter, when you multiply square roots, okay, whenever you multiply radicals, it's always outside times outside, inside times inside. Well, there's nothing on the outside of the radicals. There's nothing sitting in front here. It's not like it's 2 times the square root of 2. It's just the square root of 2. So that part I don't have to worry about. So I'm just going to multiply those two together to get the square root of 80. And then we simplify that radical, okay? Just like we've done in the past, where we're trying to look for a perfect square that is a factor of 80, which you may want your blue sheet, by the way, again, you may want your formula sheet so that you have the different cube roots, square roots, all that kind of stuff on the back side that you can refer to. So if you take a look, what is the largest perfect square that's a factor of 80? The biggest perfect square that's a factor. Ideas? Goes into 80. Abby, did you get it?
16 and 5.
Yep, should be 16 and 5. We break this down. This is the square root of 16 times the square root of 5, which now we can just go through and reduce. Square root of 16 is 4. There are no other perfect squares that are factors of 5 other than 1, and 1 goes into everything, so we don't worry about that. So 4 times the square root of 5 will be your final answer, okay? So we multiplied the radicals together, and then we simplified the answer. Okay. Now, the only new part is, now we're dealing with cubed roots, okay? But generally the same idea. This is very similar to what we were doing previously. So if I multiply those together, I get the cubed root of 80. But now, instead of looking for, and this is what we talked about last week, instead of looking for perfect squares that go into 80, now I'm looking for perfect cubes that are factors of 80, because I'm dealing with cubed roots. So in this case, what's the biggest perfect cube that goes, it's a factor of 80? Think. Perfect cube that's a factor of 80. Preferably the largest perfect cube. I think, Sophia, did you get it? Yeah, it is 8. That is the largest one that goes in. Because if you take a look, you've got 8, then you've got 27. 27 is not a factor. Then you're all the way up to 64, and then you're over 80. Okay, so it no longer could be a factor if it's bigger than what we started with. So this is going to be factored to the cubed root of 8 times the cubed root of 10. And same thing again. Once we factor, now we simplify. So the cubed root of 8 is 2. All I'm asking is, what do you cube to get 8? Cubed root of 10, the only factors of 10 are 2 and 5, or 1 and 10. None of those are perfect cubes, so we leave that alone. 2 times the cubed root of 10 would be our simplified answer for that one. Okay. Same idea though. Multiply and then simplify. Okay, that's kind of the idea that's going on. Let's go a little bit further. So first question, what do you think has to be true about the index? Remember the root, okay? What has to be true about the index in order to complete the problems above? And they were. It was given that we worked already. Cal, what do you think? What do we have? What do you think has to be true? And again, the index is the root that we're taking. Could be a prime number. It's okay if it's prime. In order to multiply two radicals together, what do you think has to be true about the index? What do you think, Parker? For example, let me go down here for a second. I'll help you out. Could I multiply those two together? Why do you say yes? No?
Wait, what are we multiplying?
The fifth root of 2 times the cubed root of 40. Do you think we would be able to multiply those two together? Why do you say yeah?
Well, because can't you do the
So good, and I'm actually happy that you said that. It's perfect. It's not right, but it's perfect. It's a perfect mistake, okay? Because I think a lot of people would think the same thing. So the idea is, if there's a number in front, if that 5 was not the fifth root. If it was 5 times the square root of 2 and 3 times the square root of 40, then that's exactly what we would do, is we would multiply those numbers in front. But what I'm getting at with this question is, what do you think has to be true about the index in order to multiply? You got to be taking the same roots, okay? So unfortunately, I can't take a fifth root and then multiply it by a cubed root, okay? It doesn't work out. Notice square roots times square roots, cubed roots times cubed roots. Here we're just about to do one more, fourth roots times fourth roots. All of those are fine. We can go through and do that and get answers, but you got to have the same roots, okay? You got to start with the same ones. Otherwise, it doesn't work out, okay? So in this case, this one is not possible because of the fact that they don't have that same index. So let's do one more. Matter of fact, why don't you do this one on your own real quick? I'll give you a minute or two here to see what you can come up with. Take the fourth root of 2 times the fourth root of 40 and see if you can simplify that down. All right, let's see what you got. Marissa, what'd you get on this one?
4,
Say it again.
4, 4,
Okay, you're close. You're very close, actually. So let's take a look. On the fourth root of 80, what's a perfect fourth that is a factor of 80? What goes into 80 that's a perfect fourth? What do you think? What'd you find? Did you find it? 16. Okay, so if we factor this, this is the fourth root of 16 times the fourth root of 5, which I think the only mistake you made, Marissa, was the fourth root of 16. Remember, what that's asking you is what raised to the fourth power is 16? And what do I raise to the fourth power to get 16? We take 2. Okay? Fourth root of 5, there are no other perfect fourths that go into 5, so that stays. And there's our final answer. 2 times the fourth root of 5. Okay? There's all we've got right there. So biggest thing I can tell you is multiply first. And again, if there would be any numbers on the outside, like these final answers are ending up with, you multiply the outside times the outside, and then you would do inside times inside. Okay, and we'll get to that. I'll show you some examples on that. But but otherwise, multiply then simplify every time. That's the idea. Okay. All right. So let's keep going then. So now let's just put some variables in with it. Okay. That's kind of how the last lesson worked as well. We dealt with just numbers first, and how do I simplify all these things? Now, and then we did variables. How do I simplify? So now, same idea. We're going to multiply, notice, fourth root, so it's okay. I'm going to multiply these two together, and then we'll simplify the final answer. Notice there's nothing in front of the fourth roots, so I don't have to worry about that. We're just going to multiply what's underneath and what's underneath. Okay? So if we go through and we work our way through, if I take the 9 times the 18, that gives me, and let me actually put the fourth root here. So we've got the fourth root, 9 times 18 gives you 162. Okay, if you multiply those. Then, what about the x's? How many total x's would I have? What power? X to the, what do you think? Yeah, what do you think? X to what power? X to the 5th. Here's where our properties are coming back in. 3 x's here, times 2 more there. Add the exponents when you have the same bases. So this is going to be x to the 5th. Y to the 7th, y to the 5th. We put those together. We get y to the 12th. And then same thing with the z's. Z squared, one more z, we end up with a total of z cubed. And so we multiply first, there it is, and now that's what I have to simplify, okay, which is kind of similar to the backside of that 6-1 worksheet that we were just talking about. It's back to what we were doing before. So same thing as what I told you last week, one step at a time. I'm going to take care of the fourth root of 162. Then we'll take care of the x's, then we'll take care of the y's. We'll just do it one thing at a time, okay? So if we start off with the fourth root of 162, 162 is not a nice perfect fourth, which means we're going to have to simplify it like we were doing before. So what is a perfect fourth that does go into 162? It's a factor. Perfect fourth that's a factor of 162. What do you think, Naomi? What do you got? It is 81. Yep, very good. So if we factor this is going to factor to the fourth root of 81 times the fourth root of 2. Okay? So we'll start there. And we'll deal with that in a second. Now I'm going to move to the x's. And here's where one of the things I want to make sure I clarify from last week. Okay? So the fourth root, how many times would, the idea is how many of these x's would come out of the radical and how many stay under the radical? Okay? How many come out and how many stay under? And the idea is, remember last week we talked a little bit about like long division? Well, how many times does 4 go into 5? How many total times? Just 1, right? And that puts you at 4 with a remainder of 1. So it goes in 1 full time, and then there's a remainder of 1, meaning 1x comes out and 1x stays in. Okay? Does that make sense, or do I need to explain that a little bit more? You tell me. Does that make sense to you? We start there. Because all I'm doing is breaking this up. I'm going to show you just, for this one time, I'll kind of show you just to make sure. So if I take x to the 5th, and let's say I just break it up, here's y. I could break this up into the fourth root of x to the fourth times the fourth root of x. There's your x to the fifth. Well, what's the fourth root? What do I raise to the fourth power to get x to the fourth? That's x. And then here's your fourth root of x. Okay, and so if you remember, I said 4 goes into 5 one time. Well, there's the 1x, your x to the first power then that comes out. And there was 1 left over. There's the x to the first power that's left inside. Okay, that's the idea of the long division, is how many x's are, x to what power is coming out and x to what power is staying in. That's the idea of what's going on. This is really what's happening here, because you're kind of factoring the x. Okay, so ultimately then we end up with times x times the fourth root of x. There's that part of it. Let's move to the y next. Now we're taking the fourth root of y to the 12th. What is the fourth root of y to the 12th? This one should go nicely, hopefully. What's the fourth root of y to the 12th? What do you think on this one? Heavy weighted. What do I raise to the fourth power to get y to the 12th? Or how many times does 4 go into 12 is the idea. Yeah, so therefore, this would be y cubed. And here's what I want you to see about it. I'm going to erase it in a second. But here's what I want you to see. Remember, fourth root is what do I raise to the fourth power to get that? Well, if I took y to the third, don't write this down. If I took this and raised it to the fourth power, do I get y to the 12th? That's what you should be kind of thinking in your head. Okay, what do I raise to the fourth power to get that? Also, how many times does 4 go into 12? 3. Therefore, y cubed is what's coming outside. And the reason why there's nothing left underneath the radical is because it goes in nicely. There's no remainder. Okay, so there's nothing left under. There's no y's left under a radical. So let me get rid of that for a second and clean that up. So this would be times y cubed. And then the last part, how many times does 4 go into 3 for the z's? How many total times, whole times would it go in? None, right? Which means we just leave it as the fourth root of z cubed. There's no z's that we can pull outside of that radical. Okay? So that we're going to leave as the fourth root of z cubed. All right. So we took care of the numbers. We took care of the x's, the y's, the z's. Now we just got to clean it up, is the idea. Fourth root of 81 is 3. Okay? So this ends up being, if I go through and we take this ends up being 3 times the fourth root of 2 times x times the fourth root of x times y cubed. I'm just going to kind of rewrite the rest of this. Times the fourth root of z cubed. So here's your final step right here. Anything that's on the outside of the radical, we said when you multiply, outside times outside, inside times inside. Here's what I was talking about. 3 is on the outside, the x is on the outside, the y cubed is on the outside. I can put all those together. I can multiply them all. So therefore, we get 3xy cubed. That's all on the outside of the radical. Then, everything that's under the radical we multiply together. So fourth root of 2x and z cubed means we have the fourth root of 2x z cubed. That stuff all is underneath the radical. And that's as far as you can go. Okay? That's as far as you can go. The process, though, that I know there's details here that obviously you got to work your way through. But the process is still the same. Multiply the radicals together and then simplify. Okay? The simplifying part is the same stuff that we were working on last week, like I said, on that 6-1 worksheet. And just take one thing at a time. How do I take care of the 162? How do I take care of the x's, the y's, the z's? Okay? If you can break it down into pieces, it makes it more manageable. Okay? Like I said, it may make the process a little bit longer, but I think it's worth having a little bit longer process if it's manageable. Okay? So just kind of a heads up on that one. Any questions on anything up here? Anything not make sense to you? General idea when multiplying radicals. Outside times outside, okay, 3xy cubed, anything that's on the outside of the radical, times anything underneath the radical. Multiply together and then simplify if you can. All right, so then let's go to dividing. That was the multiplying idea. And there's kind of two things we got to take a look at for dividing. Sometimes there's a simpler version, and sometimes there's a little bit more difficult. We'll take a look at both. So first option, again, we're going back, same thing, by the way. You have to have the same index. You can't take square roots and divide them by cubed roots, things like that. You can't take cubed roots and divide them by fourth roots. Okay, so you gotta be working in the same index. Okay, that's the first part. Now, these first two, we can clean this up a little bit, okay? Because 80 is divisible by 2. Which means, remember, I'm going to kind of take one of our properties in reverse. I'm going to take one of our properties. Remember, I just said on the 6-1 worksheet, when you take the square root of a fraction, you take the square root of the top, square root of the bottom. I'm going to do that in reverse. I'm going to turn this into the square root of 80 over 2. Okay? And the reason I'm doing that is because 80 is divisible by 2. Which means this is really just the square root of 40. So sometimes that'll work out. It doesn't always work, but sometimes that will work out where you can turn a fraction into one big square root, simplify that fraction, and now you're right back to simplifying a radical again. What's the perfect square on this one? Let's say perfect square, that's a factor of 40. Because now we've divided, and now it's time to simplify. What's a factor? What do we come up with? Kyle, what do you think? What's a factor of 40? Is it perfect square?
A perfect square?
Yep.
4?
Yeah. 4. And actually, that's the biggest perfect square that goes into 40. So this becomes the square root of 4 times the square root of 10, which we simplify. I end up with 2 square root of 10 is my final answer. 2 square root of 10 is your final answer. So that's kind of previously when we only dealt with square roots before. Now when we do it with cubed roots, still the same idea except for the very final end portion here. I can do the same starting spot here. I could turn this into the cubed root of 80 over 2. Pull that square root or cubed root out. 80 divided by 2 is then the cubed root of 40. And now that's what I'm working on to try to simplify. Okay. In this one, what's the perfect cube that's a factor of 40? Perfect cube. It is 8. Yep. Okay, so in this case, I can factor to the cubed root of 8 times the cubed root of 5. And once again, then we can simplify. Cubed root of 8 is 2. Cubed root of 5 just kind of comes along for the ride. There's nothing else we can do. So there's our answer there. 2 times the cubed root of 5. So first recommendation, when you are dividing radicals, if they're divisible by each other, you can always, that's the first thing I would say look for, is take that square root, turn it into one big fraction, simplify, and then go from there. Okay, because I'm telling you that'll be the easiest method if it's doable. Okay? However, it's not always doable. For example, square root of 10 over the square root of 3. Well, 10 is not divisible by 3. Okay? 3 doesn't go into 10 nicely, so therefore it's not really going to help us at all to go through and turn this into the square root of 10 thirds because I can't take 10 divided by 3 and simplify. Okay? So what I want you to remember back to is, we talked in a previous chapter, I think it was back in chapter 4, a little bit in chapter 5, we talked about how you don't want to have square roots in the denominator. We need to rationalize the denominator. And so the idea behind this is, we need to figure out what am I going to multiply by so that the square roots are no longer in the denominator, or the cubed roots are no longer in the denominator, okay, or whatever root we're talking about. So here's the idea. In effect, what I'm trying to do, if I want to get rid of a square root, the easiest way to do it is to square it. So here, in effect, is what we're going to do. If I want to only square the denominator, if I'm trying to get rid of that radical, I'm going to multiply by what's there. I'm going to multiply by the square root of 3. Because when you multiply something by itself, you're squaring it. That's what's happening. Okay. But as always, anything you do to the numerator, or the denominator, excuse me, you have to do to the numerator as well. So now, if we go through and we multiply, now we've got the square root of 30 over, when I multiply those, we get the square root of 9. Or if you'd rather, you could just go through then and square root of 9 if you wanted to go straight to it. You could just say that this is the square root of 30 over 3. And now we no longer have a radical in the denominator, and that's kind of what we were trying to do, is we were trying to get rid of that. If there was a perfect square that was a factor of 30, we would have to reduce that radical as well. In this case, there are no perfect squares that are factors of 30, so we don't have to worry about it. So there's my final answer. Okay. The concept here that I want you to think about, though, is you're trying, when dealing with square roots, I'm trying to square the denominator to get rid of the radical. When I'm dealing with cubed roots, I need to cube the denominator. Okay? And so I can't just go through and multiply by the cubed root of 3, because that's not going to help me. That would be squaring the denominator, and it doesn't change it. You'd still have a radical there. So here's the idea on this one. Here's the easiest way that I can help you on this one. If I'm going to cube this, that means I need to multiply by 2 more of these, right? Which, hopefully, if this is making sense, if I'm multiplying by 2 more of these cubed root of 3s, doesn't that mean I'm multiplying by the cubed root of 9? That make sense? If you're going to cube the denominator, you got to multiply by 2 more cubed root of 3s. 2 more cubed root of 3s is the cubed root of 9. And then again, anything you multiply by the denominator, multiply the same thing by the numerator. So we end up with cubed root of 90 over, in this case, you would get, in the denominator, you would get the cubed root of 27. Which, if we go a little bit further, did it work? Did I end up with a nice perfect cube in the denominator? Yeah. Cubed root of 27 is 3. Therefore, there's no radical there. So we end up with the cubed root of 90 over 3. So only difference is when you're dealing with a cubed root, you need to multiply by something that will then cube the denominator. If you would have a 4th root, we'd have to multiply something that would we'd have to raise it to the 4th power, is the idea behind it. Okay? So basically what you're trying to figure out is square roots, I want to end up with the square root of a perfect square. Cubed roots, I want to end up with the cubed root of a perfect cube. 4th roots, I want to end up with the 4th root of a perfect 4th. Okay? So that I can actually take that root and end up with a nice whole number answer that has no roots in it at all. That's the idea behind it. All right, let's throw some variables in there. Let's see what we come up with here. All right, so the first thing we have to figure out is, what am I going to need to multiply the denominator by? Okay, because here I need to end up with nice perfect cubes since I'm dealing with a cubed root. So, first thing, what number am I going to multiply by? If I start with the cubed root of 3, what am I going to multiply by? We kind of just did it. Parker, what are we going to do?
So you're trying to get
Perfect cubes.
so when we try to get 27.
That's exactly it. Yep. So what would I have to multiply by? Yep. So in this case, since I'm trying to get perfect cubes, that's kind of my final answer here. I want cubed roots of perfect cubes, which means I'm going to multiply by 9, cubed root of 9, which will then give me the cubed root of 27. So that part will be taken care of. Now we move to the x's. How many more x's should I multiply by? So that I end up with a perfect cube. How many more do I need? What is it, Debbie?
1.
Yeah, I've already got 2 x's, x squared. So I need to multiply by 1 more, so that when I put it all together, I get x cubed. And we can take the cube root of x cubed. Then, same thing with the y's. How many more y's do I need to multiply by? What do you think, Cal? How many more y's do I need in order to end up with a perfect cube? Nope. Got 1 here. How many here so that I end up with y cubed? Yeah. I need to multiply by y squared. Okay? Because again, I need a perfect cube in my denominator. So if you take a look now, if I multiply by this, here's what I end up with. Can I take the cube root of 27? Yes, I can. Can I take the cube root of x cubed? Yes, I can. Can I take the cube root of y cubed? Sure can. Okay? So this is really the key part. You figured out what you're going to multiply by, which means you got to do the same thing in the numerator. Okay? You can't multiply denominator by 1 and do numerator by something else. So we're going to multiply the numerator by the cube root of 9xy squared as well. That way we're only multiplying by 1. Multiplying numerator and denominator by the same thing, so it's kind of a fancy way of multiplying by 1. So ultimately, if I put this whole thing together, 10 times 9, this gives me the cube root of 90. X times x gives me x squared. And y squared times y squared gives me y to the 4th. So now we simplify. Okay, now we start to kind of clean this thing up. I had to figure out how to get my nice perfect cube in the denominator. The rest of it is just simplifying it down as much as we can. Okay? So for now, I'm gonna leave this alone and we'll just rewrite the denominator. And then we'll come back. So cube root of 90 x squared y to the 4th over so cube root of 27 is 3. Cube root of x cubed is x. Cube root of y cubed is y. Okay, so we took care of the first part of things, meaning I got rid of the radical in the denominator. That was kind of goal number 1. And now the only thing left to do, like I said, is simplify anything here that we can. Okay, try to simplify this down a little bit. Well, if you're thinking of perfect cubes, are there any perfect cubes that are factors of 90 that we could reduce the 90 at all? What do you think? Any perfect cubes that are factors? 8 go into 90 evenly, 27 go into 90, 64. What's the answer? Any perfect cubes that are factors of 90? No. So therefore we can't do anything with that. So that stays. In this case, because I don't have at least 3 x's, there's no way I can take the cube root there. So there's nothing I can do with the x squareds. But there is something I can do with y to the 4th. Okay? So for example, I'm going to come over here. The cube root, we said 90 I can't do anything with. We said x squared I can't do anything with. What's going to happen to the y's? And this is similar to one that we did previously. How many y's are coming out of the radical, and how many are staying under the radical? How many times does 3 go into 4? 1 whole time, right? That means y to the 1st power is coming out of the radical. And how many y's are left over that did not come? There's still 1 underneath there. Okay? Which means the only reason why that's important is because now, if you take a look, I've got a y out front here, and I've got a y down there. Now I can cancel those. And there's your final answer right there. Okay? So there was one last thing that we could do when we simplified that. So final answer to this problem. Cube root of 90x squared y over 3x. All right, let's try to do one last example here. Let's see if we come up with one, something similar to what we just did. Because again, we're getting a little bit shorter on time. We only have till 8:17 today because of the ELT. All right, last one, last example that we'll go through, similar to what we just did, just a fifth root now instead of a cubed root. So the question is, the fifth root of what, we'll go number x's, y's, okay? If I want to end up with a perfect fifth, take a look at your perfect fifth column on your chart. What's a perfect fifth that 8 is a factor of? 32. So I want to end up with the fifth root of 32, which means in order to get there, I need to multiply by the fifth root of 4. Okay? So that's kind of, if you have kind of the end in mind here, if you have the end result of here's what I want to get to, then it helps guide you of how do I get there. How many more x's do I need? Yep, so we're going to multiply by x squared. How many more y's do I need? Y to the third. Okay? And so when I do that, I would then end up with x to the fifth and y to the fifth in the denominator. Which now I can take the fifth root of all three of those things. So we're on the right track here. But I got to multiply the numerator by the same thing that we figured out. So fifth root of 4x squared y cubed gives me 3 times 4 gives you 12. X times x squared gives you x cubed. Y to the fourth times y to the third gives you y to the seventh. So we figure out what we need to multiply the denominator by so that I can get rid of the radical. You then multiply the numerator by the same thing. And now the rest is going to be simplifying this whole thing down. So once again, I'm going to leave the numerator as is for now. We'll deal with that in a second. Fifth root of 32 is 2. 2 to the fifth power gives you 32. Fifth root of x to the fifth is x. Fifth root of y to the fifth is y. So we no longer have a radical in the denominator. So the only question left is, can I simplify the numerator at all, which will then possibly cancel something in the denominator. Can I pull anything out of my fifth root? Why? How many? Close. You have the right idea. You're just getting confused a little bit, but you're on the right track. 1. There you go. 5 goes into 7 one time. Okay? So I can pull 1y out, which means a y squared. 2 y's will still be left in. Okay? So we end up with 12x cubed, and then there's a y squared still on the inside. We can take a fifth root of 5 of those y's. That's where that y is coming from. With 2 of them still there, we can't do the rest. And then again, you've got 2xy in the denominator. This y cancels that y out, and the rest is your answer. Fifth root of 12x cubed y squared, all over 2x. All right, so here's what I have for you today. Only assignment coming out of today, although I guess you could do a couple of things. So I've got a 6-2 worksheet where you're just going to practice what we've been working on, okay? Multiplying and simplifying, dividing, simplifying, okay, things along those lines. So you've got a worksheet. That's the only assignment coming from this lesson. And then I did put it together a delta math for this week. Remember the A23 delta math? That was the review assignment from last week, okay? So you should have 3 assignments either done or close to being done from last week. Series of exponents, the 6-1 worksheet, and then the delta math from last week, which kind of summarizes and wraps everything up and gives you some more practice to try to solidify your understanding. This week, you got a 6-2 worksheet, and you could start, you won't be able to necessarily do all of this, But if you want to start and do a couple of problems here, a couple of problems there throughout the week, there are things here that are multiplying and dividing that you could do right now. Okay? So let me hand this out. Other than that, once you've got the sheet, we've only got a couple minutes left. You are welcome to go. And if you have any questions, please don't hesitate to email. If you need to come in, like after school tonight or something, if you're struggling and you want to come in and go over some things, come on in. That's perfectly fine. I will help you out. And we'll go from there.